Hello everyone, October 9th. Alright, let's see what we have today. Maximum with a ramp. A ramp in an integer array nums is a pair for which I smaller than j and nums I smaller than nums j. A ramp in an integer array is a pair such that nums I smaller than nums j. The width of such ramp is j minus I. Given an array, what is the maximum width of a ramp in nums? If there's no ramp, so I have this is 1, this is 4, 0, and 5. And this is going to be 1 and 4. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so basically you want to find a pair, or you can say, let's put this one as example. So what you want to do is, for everything, you want to find the rightmost element that is bigger than this. Right? The rightmost element that's bigger than this. I smell maybe a monotonic array, something like that. Yeah, let's say we do monotonic decreasing. That won't work. Because when you pop, maybe it's not monotonic decreasing. Or maybe we need a prefix max. A prefix max. So it will be 1, 4, 4, 4, 9, 9, 9, 9, 9, 9. Right? That's a prefix max. So once we get the prefix max, now you go. Now it's 9. You want to find the first occurrence of something, the rightmost something that's bigger than it, right? So you can binary search. Ooh, maybe we should do the other way, go small. Wait, binary search, I don't think you can do binary search this way. So everyone in a binary search, like for 9 it's not gonna work, right? For 8 we can find the first occurrence of 9. Huh. So can we do binary search in reverse? Actually, I don't know. JavaScript. I mean, okay, we can do it the other way, right? We can just reverse this whole thing. right? We can reverse the whole thing, and then yeah, we do from right to left, because the results is the same, right? The result is the same, so I can reverse the array and then create the become 1 4 4 4, right? And then you binary search for each one. You binary search. Oh, in this case you can't even binary search. Ah, I have another idea. We use a tree map. So the first time you hit it, right? So this one will have something. First time I hit it, and then 9. Basically, we have 3 values for this one. 3 values, each one is the rightmost index. And for each, you'll binary search this to find the ceiling, right? To find the ceiling. Actually, it's a good question. What if it's, so let's say Java tree map ceiling key. Or null, right? It will return null. So if no, then you are the biggest. Or in this case, that will be 0, right? That will be 0. Because you need to be something that's bigger than you. Yeah, nothing is bigger than you. Then this will be null. 8 will give you 9. 1 will give you 9. This one. Actually, no, 1 will give you 4. Right? 0 will give you 4 as well. Yeah, I think this is the solution. Oh, it's 10. Okay, so for this, we're gonna do a tree map of integer and integer of what? What do we call it? We call it last indices. Okay, then for int I equal to nums.length minus 1, I large equal to 0, I minus minus, right? And we'll say int max equal to minus 1. Max equal to math.max nums I and max, right? If in last indices dot contain keys max, if it does not contain, then last dot put max I. If it contains, then we don't put. Okay, so we go through this, and then we go from front to back. Maximum, so we do 0. For int I 0, I smaller than nums.length, I plus plus, right? Then we say int oh, it's not, it's integer. Ceiling equal to last indices dot ceiling key nums I. Right? If ceiling is not equal to null, then we say res shall equal to yeah, as long as you are not the biggest one, somebody will be bigger than you, and then you will have a result. Math.maximum last indices dot get ceiling minus I and res. Return res. Okay, let's take a look. 962. Use a tree map to keep track of. Do a prefix max from right to left on nums. Use a tree map to keep track of the last index of each occurrence of new max value. Then go from left to right to find the key in the tree map that is that is barely the smallest, to find the smallest key in the tree map that is bigger, right, than the current value. This guarantees that the smallest big key has the maximum index. Okay, so we need on log n. Okay, because this is on, this will require log n. Yeah. Okay. Let's give this a shot. Hopefully we already considered all situations. Yep, we did. It's slow, but it passed. I think it kind of signifies that there is another solution because it's very slow. Alright, let's see if there's another way of doing it. I think it definitely does, because if I do that, and let's say we do another array, prefix min 9 8 1 0 0 0 0 0 0 0, right? The prefix min. Therefore, we can have, I don't know, so for 9, what if for like maybe 2 pointers? How do we use this? So we'll go, there's all the 9, right? Yeah, because this is the biggest, so as we go, it will become small. So I say move on. And then go to the biggest. Okay. So I'd say we're here and this is here. Right, now you get it. Next one, I move here, and this go. And we go to the one that's smaller. First one is smaller, so we go here. Then we know it's gonna be this. Now we move here. It's 0. Right? And then 0. It's bigger, so then we go outside, and then this will do, and then we go. Yeah, I think if we do that, it's likely going to be a ON solution. And we don't have to bother with use two prefix, use a prefix, actually use a suffix max and a prefix min. We can solve the problem in ON. Yeah, actually shouldn't call it prefix, this is a suffix. Okay, so we can say well, yeah, we do need it. But we don't need, because this is keep moving forward. This I have to create. So we can say int wait, hold a second. Why this one is not suffix max. Alright, length. Okay, suffix max length -1. Nums. Alright, let's go too many times. -2. I plus 1 and nums I. Okay, so we have suffix max. And then I equal to 0. So this is for suffix max. For, let's just do j. I0, I smaller than nums dot length. Plus. And then we're going to do int prefix min. Okay, prefix min. So now we can do prefix min. Let's call it PM. Math.min PM and nums I. Okay. So we have that. Then we shall say, and then we also have int res shall equal to 0. Right. Now we shall say while j is smaller than nums dot length, j while and nums, not nums, suffix max j is larger than PM. Right? If it's larger than PM, then we do j plus plus. If it's not larger, then we just jump out. And then when we jump out, we can say res equal to math.maximum res and j minus I plus 1. No, minus 1. Because initially I is 0, j is 0, right? And then there's shame. So immediately come out. Huh. And then next going to 8. Then the j will move forward. Yeah, because this is larger, larger, larger. Right, it'll move, move. Then it will move to here. What if it's the same? If it's the same, let me think. If they're the same, we don't move. Right? If they're the same, then we don't move. Because the goal is to find the first one smaller. No, find the first one. No, it's to consume everyone that's bigger than you, right? Consume everyone that's bigger than you. So if it's equal, and we can actually just do this. We can say if, say, PM is equal to suffix, because it can be out. So we shall do this, and if j is smaller than num star length and suffix max j minus 1. Actually, this is not necessary. Right, this is not necessary. But we do have to j needs to be larger than 0. Right, they come out, j has to be larger than 0, and a suffix max, this is larger than PM. If that's the case, then I update res. Right, then I'll update res. Otherwise, if j is 0, which means we didn't even move, then I don't do it. Right? Or if the previous is not larger than, then I don't do it. Right, so we do that, and we return res. Okay, let's give this a shot. Oop, oop, oop. 6. Pa 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 pa. Pa 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 pa. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 10, right? J should be 10. 0, 1, 2, 3. 10 minus 3 is 7. Ooh, wait, what? 3. Huh? Oh, smaller equal to. Oh my goodness, I got it wrong. How was that one passing then? This is wrong. This is ceiling I thought it's bigger. Oh my god. Oh my god, this is wrong. We have to redo this. Huh. Because I do the ceiling key. If you are the max, then yeah, because it can equal to, right? Which means, if let's do one more. I just want to confirm. Let's say we don't have these. Let's just say we have the same value. What's 999? Should be 2. Yep, should be 2. And I think my previous one will not give it 2. Hold on, I think this one is wrong. Oh, how? What was the ceiling key? Least key greater than, oh, greater than or equal to. I understood the ceiling wrong. All right, okay. Well, that is fine. Then we can just do equal to. Right, there we go. Keep going. And then again, we check this. Right. Then do we need to check this? I don't think we need to check this, because this one will always work. That's my understanding, that this one will always work, because there will be yeah, I think this will always work. Okay, I'll fix this. Yep, I do think that is the one. Right, that should give me 0. Yep, this should be faster. Yes, this is much faster. Good. 2 solutions. Oh, the first one was a little bit lucky that we got it right. We can sort. Oh yeah, I guess you can sort. Two pointers. Oh, you can do monotonic stack. Actually, I need to take a look at this sorting. So we an index array. Interesting. Oh, sort the indices based on corresponding value in the nums. Right, the small value goes first. If it's the same, we use the same. So basically, after sorting, we have an array of indices, and it's following the trend. And then Because as we go to the right, the value goes higher and higher, right? The value goes higher and higher. So we do just need to keep track of the minimum index we have encountered so far. And each time we just do the minus. Yes, yes. Okay, this is better. This is better than the one I was thinking. It's both O and log n, but mine takes longer. 2 pointers. This is what I have, and I think yes, it's exactly how this one looks like. Although you can say that you can just do nuns left. Oh yeah, that's true. You don't have to keep a prefix min. That's for everything you move to the one that's and the next one, then you can just keep moving forward. And the next one comes if it's smaller, then you can keep moving forward. If it's bigger, then you cannot move, right? If it's big, then you cannot move, which is fine, which means we can do it without using this. This is not necessary, right? All I need to do is do this. Yep. No need to use prefix min, right? No need to do that. We just go through every value in nums and compare it to the suffix max array. Okay, so that's that. Yep, I mean it's the same. I would not expect even less, but it is a better solution, I have to admit. It's a better solution, and it's deserved to be included. Alright, so last one is, because we were thinking about monotonic stack. Let's see, how do you do monotonic stack? So we have a stack. Fill the stack with indices in increasing order of values. Oh, it's pushing in the indices. Wow. If it is empty or the value is bigger, so it's a monotonic decreasing stack, which you put the indices in. Okay, so I have the indices which is decreasing, right? And then we traverse the array from end to start. And each time we hit it, if it's bigger, then hold on, I think monotonic decreasing, right? So we have the index. So that index is basically the smallest, right? It's the smallest, and if you're a big value, then you just pop. Right, you pop, pop, pop until you hit something you cannot pop. Then, yeah, because that's the first time you push in, right? Then that is your range. And the second one, if it's bigger than this, then you can pop, right? But if it's not, then you will not do. So you have that index, which is monotonic decreasing, so everything in between is bigger. But you already popped, right? You already popped, and if this is smaller, and you just, yeah, because only if it's bigger than we pop. And every time we pop, you know what? I think that is an interesting idea I want to entertain. I was trying to do monotonic earlier, but was not successful. It turns out I was just not imaginative enough. So this is the monotonic decreasing stack solution from the official solution. It pushes not the value but the index of the value in the monotonic decreasing stack. That is very important. So we're gonna do a stack first. I'll call it mon, new stack, right? For int I 0 I smaller equal to nums dot length I plus plus. Okay, we say if mon dot is empty or mon dot peak, right, nums mon dot peak, if this is bigger than nums I, in this case mon dot add I. Okay, so this is the monotonic decreasing array with indices. Okay, and then we say int res is equal to 0 for int I equal to nums dot length minus 1 I larger equal to 0 I minus minus, right? Go from right to left, pop the stack if the top of the stack is smaller or equal to nums I, and each popped indices can be used to compute the width. Okay, while mon dot is empty, it's not empty, right? If it's not empty and nums mon dot peak, if it's smaller or equal to nums I, right? If that's the case, I would say res awesome dot maximum res, and we can do I minus mon dot pop. Oh, it's beautiful, right? So we'll do this blah 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 towards the end, and then we'll return res. Okay, let's take a look. This is monotonic decreasing, and it is correct. Yeah, it's fine because it's, I mean, we can make it better by not doing we can do this without using a stack, but it's okay. It's like, oh, I like this problem. A good problem. And yeah, but I don't think it's an interview level problem because all these solutions are the same. Well, you might say the sorting is O1 log n, and that's the thing. If the interviewee immediately goes for the ON solution, then what do you do? Right? The ON solution, I mean, I went directly for ON solution. Okay, that's not true. I went for the ON log n first. Yeah, you know what? That's, yeah, we can put it in. I think we can put it in. Alright, that will be it. Good problem. I'll see you guys tomorrow. Adios.